call on you, or you can volunteer. Volunteers are fun, but I'll just call on you. So what kind of objects do we study in pre-calculus? A volunteer? What kind of objects, Colleen? Yeah, straight objects, right? Simple objects. Objects that aren't very complicated. They're just straight line objects like y equals mx plus b, or squares and rectangles. That's what we study. What kind of objects do we study in calculus? Yes, Rosa? Yeah, curvy objects. So circles, ellipses, and then any other curvy shape that you could possibly imagine, any function that you could describe, we can use calculus to study those objects, both to find the slope of the object and to find the area containing the object. It's actually amazingly sophisticated technology. Like, just say it, like, finding the slope of a curvy object is amazingly sophisticated technology. It really is, and that technology was invented in the late 1600s, early 1700s. It's also amazing technology to find the area of a curvy shape. Does it sound weird to call that technology? Normally we think of technology like computers and electronics, but mathematics is technology too. All right, so define derivative. What does derivative describe? I'd like to do that one. Yes, Nando. Yeah, slope. Right, exactly right. Derivative, we're finding a slope. And I'm just going to write this down yet. So if you start with something like f of x equals x squared minus 6x plus 9, well, then that's just some sort of parabola. And in fact, that parabola looks like this. All right, so that's your normal function. It describes a parabola. And the function itself, well, I won't give too much away here. So what we want to do then is from this formula, derive a new function, f prime of x, that will tell you the slope at every point on that function. And so the word derivative literally means to derive a new formula. And I'm just going to go ahead and write it down. The new formula would be 2x minus 6. Because calculus really is a lot of times that easy. You can just do it in your head and you just write down the derivative. So this is the original function which tells us the actual parabola and how tall the parabola is at any point. And then from that formula, there are rules that calculus tells us to derive a new formula called f prime of x. And the output value of this formula is no longer the height of the function. The output of this formula is now the slope of the function at any point. So if you want to be specific or technical, derivative means to derive from. We derive the slope formula from the height formula. But really, we use the word derivative to mean slope. Derivative means slope, because we're finding the slope. Okay, thank you. And what is integral mean? Molly? Area. Yeah, integral just means area. Now, to be fair, integral is the process whereby we use this long curvy s to integrate or take the integral of some particular function. But that process of the long s again means what word? Well, sigma is the Greek letter, which means the same thing. What did the s stand for? Sum. It's the sum. You're summing all the area under the curve. So in this particular case, let's say I wanted to go from 1 to 4. I would be finding this area. That's kind of fun. I'm finding that area under the parabola, right? So if I were to integrate this function from 1 to 4, that's what that would mean right there. I'm integrating this function from 1 to 4, meaning between 1 and 4, I want to find the area trapped below the parabola and the x-axis. I would be finding that area. Okay, well, great. So integral is area, derivative is slope. What does f of x represent? Sarah? Yeah, height. It's the height. Right? So f of x is always telling you the height of how tall that parabola is or how tall whatever function is. So when we use f of x to mean height, to be fair, what we're really calculating is the y value, or more specifically, the y coordinate of every coordinate on this parabola. So like, here's a coordinate on the parabola, and typically we write down coordinates like x comma y. But in this class, it's a lot more effective to write down the coordinate as x comma f of x. So f of x is the same as y. It just writes it in function notation. Another way of thinking of a coordinate is xy, x comma f of x, or simply input output for that function. So if I were to go ahead and input 3 into this function, like f of 3, so I'm going to input 3. 3 squared is 9. I'll write it down. 6 times 3 is 18. It's 9 minus 18. Plus 9. 9 minus 18 is negative 9. Negative 9 plus 9 is 0. And so if I input 3, I output 0. And literally, if I input 3, output 0, that is this coordinate right there, 3, 0. So that's a lot of different ways to think about what a coordinate means. And it's helpful that we're flexible in our thinking and remember all those ways so that at any given moment, you can choose how you're going to think about what a coordinate means. In any case, f of x means height, which is the y value, which is the y coordinate, which tells you that value of that coordinate. Okay, super. What does f prime of x represent? Someone who hasn't said it. Fatima? Yeah, it's the slope of the curve at that point. So f prime of x, for instance, let's look at that point 3, 0. What is the slope of the parabola at that point? What is the slope of the parabola at that point? That point's right on the bottom of the parabola. So if you were to look at the bottom of the parabola, what was the slope right there? 0. It has 0 slope right there. Whereas if I were to look at this point over here, f prime of x would tell you the slope, which would be, you can just approximate, positive. It would be a positive slope. Whereas if I went over here to a point like, say, this point right here, f prime of x would tell me what kind of number? A negative number. Okay, so that's f prime of x. And then finally, what does the long s integral f of x represent? We already said it. Let's say it anyway. JR. Yeah, the area under the curve. Trapped in between two numbers, right? It wouldn't make any sense to just say the integral. Well, okay, to be fair, there are situations in which we just take the integral of f of x. But without those two numbers, you don't know where you're taking the area, right? And even funnier, like imagine if I said from 1 to 1. What would that even mean? Find the area trapped strictly between 1 and 1. How much area is there if it's just a thin, infinitely thin slice? Is there any area there at all? There's no area there at all. You need two different numbers to be able to calculate an area. Okay, well, wonderful, folks. That's all of our terminology. We'll use that terminology for the rest of the semester. Anyone want to share any thoughts or feelings before we keep going? It's an emotional safe space. We can talk about anything. Yes, Josh?
So there's no book.
There is a textbook for this class. It's free. It's online. It's a PDF. You can download it from the Moore website. Thank you for asking, Josh. I mean, your answer has a yes and a no answer. No, there is no hardbound textbook that you have to purchase and carry around with you. Yes, there is a textbook. It's right here at the top of the Moore website. So when you log into Moore, it says it right there, textbook. That's the whole textbook. You can download it all at once. Or within every single chapter that we do, like we're about to do section 2.1, the textbook just for that section is right there listed in the whole website. Okay, thanks, Josh. Anybody else question? Just, yeah, Henry?
So I was having like a little bit of a hard time last night. You sent us a message with the requirements, right?
Uh-huh.
But then you go on to Moore. So we need to both go on Canvas and Moore basically every day, right?
Right. Yeah, I mean, Moore is just where you strictly do homework. Whereas the Canvas website just has all the information about the course, the syllabus, the expectations, what your grade is. Yeah.
And it's like in the form of an announcement, right?
Yeah. All right. Well, folks, I want to show you one thing here real quick since we were just talking about it. When we talk about finding slope, I'll often use my pen and I'll just hold it up against the function and say, okay, now what's the slope? Negative. Now what's the slope? Still negative. Now what's the slope? 0. Now what's the slope? Positive. Now what's the slope? Still positive. And I call my pen a slope indicator. It's my slope indicator. And when we draw graphs, it's very helpful if at any given point you put a dot and then you go, make a little slope indicator. And then here, and you go, make a little slope indicator. And here, make a little slope indicator. And here, you make a little slope indicator. And the whole idea is that you're holding a flat ruler up against the function, tangent, okay, tangent meaning touching at one spot, to kind of show what the slope is at that point. And so I have this website right here, Showdoor. Showdoor is a wonderful website, and it does exactly that. I wish I could make it bigger. Can I make it bigger? Kind of. Yeah, that's a little bigger. So watch. I'm going to move my point along the function that I'm looking at, and my red line is my slope indicator. So if you're looking at the black dot on the function as I move along the function, you can tell that the slope is, well, if I can get it, 0 roughly. And now the slope is positive, 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 0 at the top. It's tough to make it right at the top. Okay, roughly 0. And now it's negative, 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 and then 0 again at the bottom. And then positive, 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 0 again at the top. So that's what I mean by a slope indicator. And I think this website has a really nice visual to show what that looks like. And that's a trig function, that's a sine wave, but we could just do a parabola. Here, there's my parabola. And as I move along the parabola, you can see the slope at the bottom is 0, or at least it should be. Like, oh, there we go, 0 slope. And now positive, 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 and it's getting steeper and steeper and steeper as I move that way. Then I come back, and now over here it's negative, and it's getting more and more and more steep negative over on that side. So that's what I mean by a slope indicator. It's just a little tangent line that can more clearly show you what the slope is. Any questions about that? All right. Then, let's see, you didn't have to do any homework on more yet because we haven't done section 2.1 yet, but a lot of you already went in and sent me a message and posted something to the forum. Thank you very much. If you haven't done it yet, do it tonight or tomorrow, just sometime by this weekend. Josh?
Did you like my joke?
Oh, I liked everybody's joke. Remind me what your joke was.
So it was one language. It was I told a joke about communism, but
yeah, I love that joke. That was great. I would tell a joke about communism, but everybody gets it. Yeah, that's very funny, Josh. I like, and I had never heard that before. Okay, well then, folks, let's move along. Here's today's excitement. So the calendar, this is the correct calendar. The nice thing about the fact that we don't have those 2 Monday holidays that I thought, that I had in our calendar, it gives us 2 more class periods. So that, really eases up some stress of getting through material at a faster pace, and I was able to slow down the pace and spread out the material. So specifically, I think I might have even bumped our test day back 1 day. So here we are, January 17th. We're going to begin 2-1. We do 2-1 on a day, 2-2 on a day. I give us 2 days to do 2-3, and then we begin 2-4, and then 2-4, 2 days to do 2-5, and then we take our test. So I think it'll be a really good pace. Okay, so what else? I think that's it. I already told you the pirate joke, right? Okay, this is one of my all-time favorite jokes. Where does the general keep his armies? Hold on, Josh, hold on. Continues. Where does the general keep his armies? In his sleeves! Yeah, that's the whole joke. So I taught my daughter this joke. She's 2.5 years old. And for a while, she would say, in his sleeves. But just recently, she changed the joke. And now I say, honey, where does the general keep his armies? And she says, in his sleeves. Which is like even funnier. So it's wonderful. All right, well now, everybody had a good laugh. Now we're ready to start learning some math. So, actually review the syllabus quiz. So everybody, I asked you to bring today your syllabus quiz as well as your personal info sheet. So let's just read through the syllabus quiz real quick. I'll call on you to give me an answer. First question, I need to bring a what every day to class, Holly? A calculator. By the first week of class, I need to log online to the website called what, Josh? More. Notes packets are always worth 20 points, and I'll lose how many points for every problem blankly and completely solved? Yeah, 1 point. Practice test is worth 20 points, and I'll lose what for every problem blankly and complete, JR? Don't just 1 point, still. Yeah, just 1 point. Okay, more video assignment. I'll watch the videos when, Juan? Before class, ideally. So, I'm not trying to guilt you if you didn't, but ideally you would have already watched the videos for 2-1 today, and you would have already flipped through the textbook for chapter 2-1. And even if you didn't understand it all, it put a lot of information into your subconscious brain and prepared you to more readily assimilate material today. So hopefully you watched it. The online practice assignments, they're always due when? Sarah? Oh yeah, it is Tuesday, huh? Because Tuesday is the day of our class. Yeah, it's always due Tuesday. Yep, always due Tuesday, the week after we do it. So this week we're only doing section 2-1. So next week on Tuesday, the only thing you have to do is 2-1. Okay, how many late passes do you have? Yeah, 10. I gave you 10. Even though the syllabus says 5, or did it say 10? Oh, it says 10. Okay, good. Well, I gave you 10. And each late pass, before the assignment is due, you have to go in and click late pass, and then it will give you an extra week. Right? Because sometimes we get busy and sometimes things happen. So you can extend your due dates if you need to. Test. If I'm not in class on the day of the test, I will receive a what, Molly? A 0, right? You have to be in class on test day. However, if you're going to be absent on the day of the test, you have how many opportunities, Rosa? Just one to take the test at the testing center within 3 calendar days of the test date. So if an emergency happens on a test day, and by that I do not mean you just don't feel ready, right? If you just don't feel ready, I'm very sorry. You should still come take the test. And if you just don't feel ready, don't tell me that, right? Like if you're just gonna be like, oh, I'm sick, right? Don't tell me that. Just say you can't make it to class, and then you have 3 calendar days to take the test. But theoretically, you shouldn't be using this just because you don't feel ready. You should still come in and take the test. This is strictly if your car breaks down, or you have to pick somebody up, or there's a family emergency, right? So there's just a little bit of lenience, but generally speaking, you have to be there on the day of the test. Okay, final exam. I'll keep all of my what, Henry? Yeah, all of your tests so you can study and review them before the final. All right, I will sign in and be in my seat at the start of class, which is what time, Rosa? Yeah, 11. We start class at 11. I'm allowed up to 2 tardies for free. Starting with the 3rd tardie, I'll lose what, Colleen? 5 points off the final exam, which, by the way, is 2.5%. So that's 2.5% off the final exam. So let's just say that instead of being tardy twice, which you're allowed to be, you're tardy 6 times. Okay, that's 4 times more than usual. 4 times 2.5% is 10%. So if you're tardy 6 times, you just lost 10% off your final exam grade. Brought you from like a 90 to an 80. Maybe that's perfectly acceptable to you, right? 10% is not that much off of a final exam, considering the final exam is only worth 20% of your grade. So I just want to put it in perspective. 5 points might sound like a lot. It's not a terrible a lot, but I'm hoping that it's enough to convince you to get here on time. Okay. I'm allowed up to 2 absences for free. Starting with the 3rd absence, you'll lose what? Under? Yeah, 5 more points, same thing. I can be absent a maximum of 5 times, excused or unexcused. So it doesn't matter what it is. Maybe you just sleep in at 11 o'clock. I don't know. You can be sleeping in. Or maybe you have a doctor appointment, or maybe some emergency happened. In any case, on your 6th absence, you must meet with me during office hours to discuss your progress. Otherwise, you will be, what? 1? Yeah, you're dropped for withdrawal. Every once in a while, I have people vanish on me. Right? They just vanish. They stop attending class. They don't respond to my emails, and I'm left feeling, very responsible for them. I want to help them pass the course. I want to get them back in here and keep doing the class. But if you vanish on me, you vanish on me. And so I withdraw you from the course. So the key thing is you need to talk to me and let me know what's going on. I know that won't be any of you, which is wonderful. Does someone have a question, Rosa? Okay. Okay, I can earn extra credit for perfect attendance if I have 0 tardies or earn how many bonus points? 2. Yeah, 5 bonus points for no tardies and 5 bonus points for no absences. Before the day of what? I will come into office hours for a 5-minute chat with Mr. G. Before the day of, sir? Yeah, your first exam. So you have a few weeks. Just come into my office sometime. And remember, I have office hours right after this class, so you can just come with me to my office and then you're done. Josh?
So it's very
Yeah, you can come today after class for office hours. Okay, and then if I earn less than what on any test, Mr. G will record my grade as a 0. If you earn less than 70%. So if you earn less than 70%, I put a 0 in the grade book just as a placeholder to motivate you to get into my office to review the test. After we review the test, I'll put your grade back into the grade book. The idea is I want to help you review such that we review the test so well that if I gave you the test again, what would you get? I mean, hopefully an A, but definitely a passing grade at the very least. Not that you get to take the test again. You don't get to take it again. But the point is that we'll review it. That way you know all the material. Because the class is cumulative. Everything builds on itself. So if you really bomb the first test, that's going to make the whole rest of the class harder. So we need to sit down and review and help you get caught up. Okay, wonderful, folks. So you can give that to me at the break, as well as your student information sheet. So let's go ahead and begin. You can all have out your, we're going to look at the what does a derivative find sheet first. And so, as we said, derivative, on the one hand, means slope. On the other hand, it means derived from. And if you look it up in the dictionary, it says an expression representing the rate of change of a function with respect to an independent variable. Whew, that's a doozy. Listen to that again. An expression representing the rate of change of a function with respect to an independent variable. All that just means an expression representing the slope. Because rate of change is a technical term for slope. It's the rate that the function is changing up and down. So in general, derivative means slope, means rate of change. So if you see the word rate of change, it means slope. There are lots of synonyms in this class. So derivative, slope, rate of change, they all mean the same thing, they mean slope. Okay, so we're going to look right up here at the top. And it says, recall the definition of slope. What does slope measure? Like, if we could come up with a couple of easy English words to say what slope is measuring, what is slope measuring? Josh?
Steepness.
Yeah, steepness is a great word. That's actually the word I was going to use. Does anyone else have a different word you want to use about what slope measures? I think that's fine with it. That's a nice, simple English word that anybody on the street would understand what you're talking about. How steep is something? And if you're going for a hike, how steep is the hike? If you're going to go skiing, how steep is it? We even have words when you ski. You've got like a bunny hill, and then you've got a green, and then a blue, then a black, and a double black, right? All those words measure steepness. Okay, and it's always a what? So slope is fundamentally and always everybody's favorite F word, a fraction. Right? Slope is fundamentally a fraction. Slope is not a single whole number, it is a fraction. All slopes should be represented as a fraction. So then, what's the definition? Do you all recall the letter M? What does M stand for? Slope. Y equals mx plus b. M means slope. So M is, let's go ahead and look at some definitions you've learned throughout your life. What's one definition of slope you learned? Measure or run. That's kind of the classic one. It's the one every school child learns starting from elementary school through junior high, and it's in a lot of textbooks. I never use this definition because it's misleading. What does the word rise make you think you're always doing? You're going up, but you're not always going up. Sometimes you're going down. Sometimes you're neither going up nor down. So rise isn't a great word. And run, what does run mean? Well, I don't know. You're running. But, theoretically, that means you're moving sideways, right? So a better two words would be vertical and horizontal. Those words are at least more specific English words that allow for vertical means up and down, not just rise. And horizontal definitely implies that it's a horizontal line. Okay, well, in calculus, instead of using the word vertical and horizontal, we actually use a technical symbol. Okay, vertical movement means that you're going up and down, and it's the change in your y coordinate. Right, the y-axis goes up and down. And so we're looking at the change in your y direction. And there's a Greek letter, delta, which means change in, and then we write y. It's the change in your y variable. So how much have you moved in the y direction? That means change in y. Likewise, if you want to look at the change in your x direction, how much have you moved left or right? You then use the delta, that's the Greek letter delta, that means change in x. That's something that you might have seen in some textbooks already, but definitely in calculus textbooks they say this. Now, the triangle, for some people, you don't want to draw a triangle over and over again, or maybe it's confusing, like what's that triangle? We don't use the Greek alphabet anymore. So instead of the triangle, which is the Greek letter delta, we use D, which stands for delta. D stands for delta. The Greek letter delta, which was the original way that they started doing calculus. The nice thing is D also stands for derivative. Yeah, I don't think it stands for distance. It could. It could stand for a lot of things. But it stands for derivative as well, which derivative means slope. And this is what we're talking about, is slope. But D technically, I believe, comes from the delta, the Greek letter delta, which was originally used to represent change in y, change in x. Change in y is vertical motion, change in x is horizontal motion. Okay, so these are some technical definitions that you might see in a textbook. My definition, which I like to break down into simple English so that we can communicate with each other. When I talk about vertical movement, going up and down, I literally just say slope is the up-down over the right-left. And I have to say it in an accent like that because it's so much fun. That's slope. Slope is the up-down over the right-left. So when you're looking at a fraction, all slopes are fractions, and you're looking at that fraction, the numerator is telling you how far you went up, down. And the denominator is telling you how far you went left, right. So we might as well remind ourselves that on a coordinate grid, on the x-axis and the y-axis, up is always positive and down is always negative. That's not a good spot for that. Put it over here. On a coordinate grid, up is positive, down is negative, right is positive, left is negative. So when I talk about slope being the up, down, over the right, left, then up is positive, down is negative, right is positive, left is negative. So Those are lots of different ways to define slope. What you'll notice about every single one of those definitions is that every definition is a fraction. Okay, so that said, what are the 4 basic types of slope? Slope, we already said this once, but slope can be positive, slope can be negative, slope can be 0, and slope can be undefined. All right. So now that we've said all that definition of up, down, over the left, right, what I'd like everybody to do now is to practice reading this out loud, as if you were giving directions to a friend, someone you cared about. So instead of saying the slope is 5/3, you would tell them, let's see, the top number is up, down, it's positive, so that's up 5. And then the bottom number is right, left, it's positive, so it's right 3. So you would say up 5, right 3. And that would be a very friendly way to communicate to someone who's your friend, right? Instead of just saying the slope is 5/3. Because a lot of people, what does that mean, 5/3? But if you say on a map, go up 5, right 3, it's very painfully obvious how you're supposed to go, right? Okay, so that's up 5, right 3. I'm going to go around the room and let everybody try. Henry, how would you read that in English? Oh, and let me put it down right here. Okay, so this is the up, down, where again, up is positive, down is negative, and then the right, left, where right is positive, left is negative. So Henry, how would you read this one?
Up 6.
Perfect. Up 6, left 2, that's how you read it in English. Rosa, how would you read this one?
Down 7, right 4.
Perfect. Down 7, right 4. That's how you read a slope. How about this one, Molly?
Down, left, 5.
Perfect. That's exactly right. Down 8, left 5. How about this one, Patrick? Oh, this one's tricky. There's a little negative sign floating out in front there. Where does that negative sign go? I mean, first of all, folks, since it is negative, we absolutely know the line must be going like that, right? It can't be going up. It can't be going sideways. It must be going down. So where does that negative sign go? Does it go with the 4? Does it go with the 9? Or does it go with both? I heard a lot of different possibilities. Rosie, what did you say? Let's try that out. If I put it on both, then what's a negative over negative? A positive, and now it's no longer a negative at all. So it can't be both, but thank you for saying it, so we can prove it to ourselves. Well, now that's interesting. Very good, Sarah. I'm glad you got that. So this one is down 8, left 5, right? So watch, if I start right here, and I go down 8, left 5, it is in fact a positive slope, because a negative over negative makes a positive, and it in fact is a positive slope. So it's subtle, isn't it? This is subtle. This is tricky business. Okay, so where do we put the negative? Since it's not both, you don't put it on both. You can in fact put it on either. You can choose to put it in one or the other, but not both. I personally will always put it on the top number. That's just how I do. So I'm going to scratch that out and put it right there. So now read that to me. Who's going to go faster? Up, down, over the right, left. Down 4. Right 9. Very good. Because that 9 doesn't have a sign in front of it, so it's positive. So yeah, down 4, right 9. Now let's just pretend right here. Down. If I start here and I went down 4, right 9, it would look like this, which is a negative slope. What would happen if I put that negative sign here? Read that one to me, Sarah. Now how do I read it? Up 4, left 9. Watch what happens. Up 4, left 9. It just continues the line. Right? So whichever way you interpret it, it's fine. You can put it on top or bottom. They're both going to give you the same interpretation and the same line. Okay, very good. How about this one then? Back to you, Colleen. Where do I put the negative sign? Sure. On top sounds great. That's what I would do. And then how do you read it? Down 3, right 8. Perfect. And Josh, if you just happen to want to put it on the bottom, how would you read that one? Perfect. Up 3, left 8. And now this one. Now that you got a tricky one. Is that a fraction? 9 over 1. And then how do you read it? Up 9, right 1. Now watch this, folks. A positive over a positive is positive. We know that this slope is positive. It's going like that. Up 9, right 1. But isn't a negative over a negative still positive? Could I choose to interpret it that way? I could, in fact. So now how would I read that, JR?
Down 9.
Very good. And keep in mind that if I just kept it with the 9 over 1, if I start here and I go up 9, right 1, that's this. But if I do what JR just did and I say down line, left 1, down line, left 1, it's still the same line. So there's a lot of flexibility in how we do this. Finally, what's this slope? 1?
Right.
Well, no. First make it a fraction. 0, 1. So now how do we read that?
0 or don't 0 and right 1.
Yeah, okay, perfect. You were correct, by the way, in the beginning. You said just right 1. That's correct. So if you're starting right here and you go up nothing, right 1, up nothing, right 1, up nothing, right 1, up nothing, right 1, what are we making? We're making what kind of line? A horizontal line whose slope is 0, which we already knew. Horizontal line is 0. Okay, so folks, that's how we read a slope. The up, down, over the right, left. And that way you can communicate the slope very easily in English to your neighbor or to another person. Okay, what does m equal 1 represent? Like, everybody draw a little coordinate grid here with your x and your y. 1 is really what? 1 over 1, which means up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Which means I'm making a perfect staircase diagonal. Right? It's what exactly cuts that first quadrant in half. And if I turn it around and I say -1, -1, which I'm allowed to do because negative over negative is still positive, then I'm going down 1, left 1, down 1, left 1, down 1, left 1, down 1, left 1. And so what does the slope m equals 1 represent? A perfect diagonal line that cuts that quadrant in half. So you could call that kind of like the midway. Like a slope could be pointing straight at the x, or the slope could be pointing straight at the y. That's kind of like your spectrum of positive slopes, right? Because otherwise down here you'd be looking at the negative slopes, whereas up here that's your positive slope. So m equals 1 cuts the positive slopes in half in the first quadrant. So what does m greater than 1 represent? If I go bigger than m equals 1, what would we call that kind of slope? Just in English, like a word, you'd say, if you were skiing or hiking, that's fairly steep, right? Whereas what's m less than 1 represent if you're skiing or hiking? Not so steep, maybe shallow. So let's just have that idea. Over here, m less than 1 is kind of shallow. You know, it's easy, it's not very steep. Whereas m greater than 1, you're looking at a fairly steep one. Whereas m equals 1 is a perfect diagonal. Much like a staircase would be. Okay, this is just to build an intuition. Like if somebody said to you, consider the slope 7 halves. Like a lot of times if somebody said, consider the slope 7 halves, your mind just kind of go blank and you hear a wind rushing sound. Like, well, what is there to think about the slope 7 halves? But we can think, well, 7 halves, if I were to simplify that, that'd be 3.5 over 1, which is 3 over 1. 3 over 1 is bigger than 1, so it's fairly steep. Right? 7 halves is a fairly steep slope. Whereas if somebody said, consider the slope 1/8, you'd say, well, 1/8, I mean, that's a lot less than 1. 1/8 is up 1, right 8. That would be like this. So that's fairly shallow. So my goal here is that you would have some intuition in your head about what these slopes mean, and you could picture it in your mind right away. So if I just said, hey, Henry, consider the slope 9 halves. Is that steep, shallow, or in between? It's fairly steep, right? And then if I said, hey, consider this slope, 3/15. Sarah, you're fairly shallow, right? Especially because you can simplify it to 1 over 5, and then you know that you're only going up 1, right 5, so that's fairly shallow. Okay, so hopefully this is building your intuition for us to talk about slope, which we're going to talk about for the whole rest of the semester, is talking about slopes. So turn the page, and now you go ahead and everybody try this out with the up, down, on the right, left, and go ahead and let's calculate some slopes. What I'd like you to do is use the definition of the up, down, on the right, left, and calculate a slope between these various points. So count out the slope from K to D. So come on over here, find K, find D, and then do the up, down, and over the right, left, and write down what the slope is. Do that for these 4 problems right here. And if it helps, you could even start by writing up, down, over right, left, and then start filling it in, because that's your formula. And remember, you're starting at K, and you're going to D. And so if I might, just as a recommendation, you always do the up, down first, because you do the numerator first. So you do the up, down first. So if I was starting at K, I would draw this arrow to show my up movement, and I would draw this arrow to show my right movement. And then I would get the numbers, put it into the formula, and simplify. Josh? What? Oh, okay. All right, so everybody go ahead and do those 4 problems. Let's walk around. Oh. And keep that one to fact. Yeah, because slopes are inherently fractal. You don't have to erase it, just put it over. Yeah, there you go. Yeah, very nice. Perfect. Yeah, very nice. If you get a slope that can be simplified, go ahead and simplify it. And when you simplify it, make sure you keep it as a fraction. Oh, very nice. These are all great verbal descriptions. Now go ahead and actually write down the fraction as well. Yeah, same thing. This is great. I really like they wrote it out in English. Now it equals and put the actual fraction. Yeah, very nice. Super. Yeah, very nice. Once you all did that so quickly, I can see that this is too easy for you. You're saying, Mr. G, let's make this harder. Come on, let's ramp it up. Let's get to the technical stuff. Okay, then I'll go ahead and call on some folks for some solutions here. What was the slope from K to D, Nando?
2 over 1.
Yeah, 2 over 1. It was up 4, right 2, which simplified to 2 over 1. Which by all means, you can simplify it to 2. It's just 2 is no longer a fraction, and you just lost the ability to read it as up, down, over the right, left. So 2 over 1 is best because you can still read it. What was the slope from D to C, Colleen? Yeah, so from D to C, wait, say that again.
Down.
There you go. There's down 3, right 2. So what's the final answer? If you say 3 over 2, that's incorrect because that's a positive fraction which goes up. But this is definitely going down. So you need to say negative 3 halves. Yeah, very good. Negative 3 halves is the slope. Now keep in mind, when you just say negative 3 halves, you just lost all that good English interpretation. So when you say the slope is negative 3 halves, that's true. That's how you would say it. The slope is negative 3 halves. But then you want to immediately be able to go back into your brain and say down 3, right 2. Right? Make it concrete. Negative 3 halves is the answer, but the interpretation is down 3, right 2. Okay, what's the slope from N to P? 1? Yeah, 0 over 1. You went up nothing, right 1, which equals 0. And sure enough, that was a horizontal line, and that gave us exactly the slope we expected, which was 0. Okay, then what's the slope from C to A, Molly? I'm sorry, I won't call on you. You haven't done that one yet. Okay, who's already done it? Sarah? Get down 4. And write 0. Yeah, so 4 over 0, folks. This is the exciting moment right here. If you type that in your calculator, 4 divided by 0, what does it tell you? Error. And error is exactly why we call this slope undefined. It's undefined because it is undefined. You cannot, your calculator won't tell you what 4 divided by 0 is. So that's why we call any vertical line undefined, because the slope literally is undefined on your calculator. So it's not just some word we use, right? 0 is not just some word we use. Literally, that's the calculation you get from the fraction, 0. And undefined is not just some word we use. Literally, that's the calculation you get from the slope formula. Okay, very nice, folks. So, slope, slope, slope. These next couple problems are just to remind us how to use the slope formula. And to tell you the truth, the slope formula is calculus. The slope formula is where calculus came from in terms of the derivative. Not the integral, but the derivative. So this is really important that we all know this formula and we have it memorized. So first of all, you see I already gave it to you. M equals y1 minus y2 over x1 minus x2. Can you write it differently than that? How else can you do it, Nando? Yeah, it can be y2 minus y1 over x2 minus x1. But that doesn't matter. Can it be y2 minus y1 over x1 minus x2? No, that would just be wrong. Yeah, the numbers have to go in the same order. 1, 2, 1, 2, or 2, 1, 2, 1. Totally arbitrary, it's up to you. But that's the formula. So now, how do we do a really nice job of doing the slope formula? Well, here's what we're going to do. First, label the coordinates x1, y1, x2, y2. I cannot stress how important it is to label your coordinates ahead of time because we'll be doing some complicated things, and it's always helpful to label. So then what you do is you write the formula first. M equals, I always do y2 minus y1. It doesn't matter which way you do it. I do y2 minus y1 over x2 minus x1. And then, very important, I write it empty. I write the formula empty. This formula is a big fraction with a minus and a minus. That's what the formula is. It says to create a fraction, and in the numerator, subtract 2 numbers, and in the denominator, subtract 2 numbers. So I write it empty. Why? So that I can now plug in my numbers very carefully and slowly. So what's y2? No one can shout it out. What's y2? 8. And what's y1? 4. And what's x2? 5. And what's x1? 2. Right? That's what it looks like to write a formula empty and then fill it in carefully. So now we just subtract, we get 4 over 3, and that's it. Then we're done. How do you interpret that slope? Read it in English for me, Wilson. Perfect, up 4, right 3. Okay, we can do it one more time. So, yes, great.
So I did the opposite, so I got -4.
Great, Rosa did it like this. Rosa did 4 minus 8 over 2 minus 5, which gave her -4 over -3, and then negative over negative is positive. So yeah, so either way works, and that's why it doesn't matter how you write the formula. Very good, Rosa. Thanks for sharing that. Okay, everybody, you can go ahead and do the next one. Yeah, in fact, everybody go ahead and do the next one. You do not need to do the last 2. Just do the next one. Fill your coordinates, write the formula, let the formula empty. Plug in the numbers very carefully. You will have a double negative in your formula. And as you know, a double negative becomes positive. Great. I see a lot of people having the answer -1/2. I got -4 over 8, which simplifies to -1 over 2. So check your work, and then how do you read that in English, Josh? Perfect, down on right 2. Okay, now, these second 2 I said you didn't have to do, for good reason. Just look at them. What do you notice about this pair of coordinates here? Yeah, they both have a y-coordinate of 3. So instead of actually doing the whole slope formula, make a little sketch. Say, hey, that's -4, 3, and 2, 3. Even a really simple sketch that you don't even have to make tick marks. You don't even have to go tick, 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 tick. You can just say, okay, left 4 up 3, right 2 up 3. Immediately you know that the slope is 0 because it's a horizontal line. Likewise for this last problem. You look and what do you notice about these coordinates? Yeah, they both have an x-coordinate of -10. So again, make a little sketch. You just say, hey, if I go left 10 up 2, and then I go left 10 up 8, well, those points are right on top of each other. I don't even have to go tick, 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 tick. You can just make a very simple little sketch, and you know automatically that the slope is on the bottom. All right, super. Again, maybe this feels easy. I hope it does. Maybe I hope you feel confident right now. You're like, okay, I can do this. Because these are the concepts we'll be using for the rest of the semester, and I want you to feel really confident about just interpreting a slope, doing a slope, and visualizing a slope. So, next to the page. Oh, hey, questions, thoughts, feelings? Who has a question like that? Anybody? Okay.
So the definition is slope of fraction.
Yeah.
I know it's
Well, that's a good question. I've never seen an imaginary slope. I think slope is always a real number. But that's a great question. I've never even considered the question. I'm going to go home and think about it. But I think it's real. Okay, so here we go. We've got this curve here, and it's not a straight object. It's a curvy object. And all we want to do is just label the curve at all those points with reasonable values of slope. Right? Now remember, m equals 1 is a diagonal. Steeper than that is a number bigger than 1. And shallower than that is a fraction less than 1. Right? Because to be less than 1, you'd have to be a fraction, a big denominator. And to be bigger than 1, you just have to be bigger than 1. So everybody, let's go in here and make some slope indicator lines. So on the dot there, make a little slope indicator. You're like, okay, that's the slope right there. And then label it with a reasonable value. What's a reasonable value of slope for this? I'm going to start in Back right, Colleen, what's a reasonable value of slope? A reasonable value of slope where m equals 1 is the perfect diagonal, shallow is like a fifth, and then steeper is like a whole number. I think 1 sounds good. Does everybody else feel like 1 is reasonable? I mean, it looks like a perfect diagonal to me. I think it's reasonable. I don't think anybody's going to say, oh, you're completely wrong. Right? I mean, 1 is reasonable. You might have said, no, it's a little steeper, a little shallower, but that's a reasonable answer that most people would agree with. Okay, how about here? Make a little slope indicator. You go, and what's that slope, Josh? 0. That seems very reasonable. You might say, oh, no, I think it's very subtly increasing. Well, maybe, maybe not. But I mean, 0 is a pretty good rough answer, right? JR, how about this one? Make a little slope indicator. What would you say that one is? It could be -1. That seems very reasonable. I buy it. Okay, go to the next point. Put a little slope indicator. Now, because JR has told us that this one is -1, is this one steeper than that one? It is steeper. You're now going more downhill. So the next person cannot say -1. Right? They're going to have to say something steeper than that. So what's something steeper than -1? 1?
-3?
Yeah, -3 sounds good. Anything steeper, -3. So -3 or 1. Okay, move on to the next point. This one is steeper yet. Well, I mean, this whole thing is getting steeper and steeper, I believe. Now, you have a good point, Josh. Is it? I don't know. Right? We're just approximating. So who'd like to say the value of the next slope? Roughly, Molly? Sure, -4. Again, we're just doing approximations, right? We're just trying to be reasonable. Okay, way down here, we got this little point that's almost at the bottom, but not quite. So what would you say that slope is? Josh? -0.5 sounds great, but I'm going to leave that as a fraction, -1/2. Yeah, I would say that one was a little shallower. That was shallow. And then the one at the very bottom, what's this slope down here at the bottom? That's it. One at the very bottom. That's it. 0, yeah, absolutely, it's 0. It looks like 0 to me. I mean, it could be marginally a little to the right or left of the bottom point, but yeah, the very tippy top of a curve is going to be slope 0, and the very bitty bottom of the curve is going to be 0 as well, right? Okay. Now, I know my phone just went off. That means we're going to take a break. But let's just finish. I just have one more graph to look at, and then we're going to start our actual more practice. So, one last thing to consider right up front is about how to interpret a slope. This is very exciting, okay? Because when we draw XY axes do have labels from time to time, right? It could be like if you're looking at your income over time, that could be like dollars, and that could be like years, right? So we typically have labels on our coordinate grid, right? And so if I were to say, hey, the slope is the change in y over the change in x, then what's the unit of my y-axis? Dollars. And then what's the unit of my x-axis? Years. And so what did I just produce? By calculating the slope of this graph, I just found out my dollars per year, my income. That's how much money I make. So isn't that interesting? On this graph, the slope represents how much money I make per year. That would be the interpretation of that slope. So let's look at this one. What is the unit of our two x and y axes? Everybody go over here by m equals delta y over delta x. And notice now I'm using this definition because I don't need to go into the whole up, down, right, left there. I'm not actually calculating a slope right now. I'm just thinking about what does the slope mean? And so what's my y unit? Yeah, distance in feet. I'm going to write both just so I keep them both in mind. Distance in feet. And what's my x unit? And time in seconds. So we actually have two different interpretations going on right here. So if I were to calculate a slope, and I said slope equals 1. 1 what? 1 of what? One of what? What are we talking about? So I look at this, and on the one hand, I would say, oh, the slope represents this thing, which is feet per second. Right? So we're saying, how fast is this object moving? It's moving at 1 foot per second. How fast is 1 foot per second? Moving at 1 foot per second. Right? Whereas if I were to be somewhere else, maybe a little steeper, maybe that slope is 2 over 1, then I'd be moving at 2 feet per second, right? So every one of those slopes now, because it's in the unit of feet per second, is representing a speed. So that's interesting. Now look at this one, distance over time. What is distance over time? In general, what is distance divided by time? Yeah, it is speed. Now how do we know that for sure? Do you all remember the formula d equals RT? What is d equals RT? Distance equals rate times time. Here's d over t. Let's go ahead and divide off the t. There's my d over t. So distance over time is a rate. So very literally, this is a rate. This is a velocity. What kind of velocity? Feet per second. So this is very interesting that as we go about calculating all these slopes are not just unitless slopes. They have units, and we'll interpret those units and think about what did I just calculate by saying the slope is 2 over 1, it's 2 feet per second, something like that. All right, folks, that was great. So here we go. That was essentially a warm-up. I'll never collect it, but you can take it home, put it under your pillow, keep it for the rest of your life, give it to your kids. It's your core foundational concepts to study calculus. So now, what I've done now is giving you photocopies of problems that I took straight out of more. So now if you flip to the next packet, which is 2.1, those are the homework problems you're going to see and more for section 2.1. They are not literally the same problems you'll see in section 2.1. The numbers will be different, but these are the types of problems you'll see in your homework in 2.1. So what we're going to do in general is I will take the problems from more, put them on paper for all you to have. I'll put it on my screen here, and we'll work our way through the problems and try them out together. And that way, when you go home, you'll have these notes, and you can work out the problems on the computer very easily. Also on a scratch sheet of paper, right? You show your work. But this will be your template to remind you how to do the problems. So I think now it's a good time to take a break. The time's 11:55. Let's come back to 12:05. Again, the only rule at a break is you gotta get out of here at least once. Just leave the room, get your blood flowing. If you have any questions, I'm still here. You can come talk to me. Hey, Molly.
Hi.
Well, yeah, and if you would, folks, bring me your personal info sheet as well as your syllabus quiz. We'll just make 2 stacks here. Thank you, Josh. Oh boy, apple juice. That looks good. Thanks, Sarah. You can keep the calculus. Yeah, there you go. Did I what? I did. In fact, here, I'll show you. We just had a boy just in July. Here we go. So this is Aloysa, who we had 2.5 years ago, and then that's Augustus, who we just had a couple months ago. Yep, so now we got 2 kids.
I have a
Yeah, that's wonderful. Congratulations. Oh, just in August?
Yeah.
Oh, wow.
Well, when I was in class with you,
You're pregnant, right?
yeah, I left and then over the summer, I took summer classes. August, I had her, so I didn't come back right away because I didn't take it with our fall because I had her. I didn't know what day, like, she was, my due date was the 25th, so I was like, I don't know if I'm going to have her by that time, so I just started classes like the 8th.
I think that's very reasonable. I took a little time off when we had them as well.
Yeah, that's good.
Yeah. Cool, Rosa. Give you congratulations. Oh, thanks, sir. Oh, we get anytime. Are you in high school? I had no idea. Way to go, man. You're taking calculus. This is great. Okay, what do you want me to sign? Just for history tonight? Now, I tell you what, I'm more than happy to sign this for you every single time. But all the other high school students who I've ever had, they normally just have me come in like after like halfway through and sign a date signature, or they just have me sign it all. But if you want to keep bringing it to me, 1 week at a time, that's fine. It's up to you. Thank you. All right, folks. I don't see JR, but hopefully he's on his way back. Let's begin. So this is the first thing that I'm collecting from you, right? So this is our basic class structure that we'll go through these practice problems that are similar to what you have on your online homework. You'll go home and practice your online homework. And on the day of the test, I collect all of these notes packets from them. So this is packet 2.1. On the day of the test, I collect 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. So what I encourage you to do then is write down everything I write down. All right, so if I write it down, it's important, so you write it down. And that's essentially what I look for when I collect them, is that I see lots of notes and you fill everything in and show all your steps. All right, hey Jay. So, I was a top mathematician, SU, to find average rate of change. So, again, that word rate of change. What does rate of change mean? Slope. So, there's two different ideas of rate of change. You've got the average rate of change and you have instantaneous rate of change. Let's just go on over here and draw a little drawing to see what we mean by this. Let's say you have a function, and our function is going to look, say, like this. All right, it's just an upside-down parabola. This is our function, f of x. We could even say what it is, just for fun. I'll say that it's x squared minus 7x plus 8. It doesn't matter. I just made up a function. The point is that, actually it's negative x squared there. So we have an upside-down parabola. And if I want to find the average rate of change, that means that you choose any 2 points on the parabola and you draw a secant line. There. That is a secant line. A secant line cuts through a graph at 2 points. And so if I find the slope from here to here, I'm finding the average slope on your entire journey from this point to this point. Obviously, the function itself doesn't actually go straight across. The function goes up, steeper, steeper, hits a 0 point, and then becomes negative. Right? The actual slope of the actual function is positive, 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 0, negative, negative, negative. Whereas what I'm saying, the average rate of change is that the net result is that you have positive, positive, positive. That's the net result. If you compare where you start to where you finish, the slope is positive. Even though on the actual journey, you actually start with a positive slope and then 0 slope and then a negative slope, you have more positive slope than negative slope, and so the average is positive. So when we say average rate of change, what we really mean is the secant slope through 2 points. Okay. You can say that the average rate of change, the secant slope, is a lie. Right? Does the function really do that? Does the function really go like that? No, it goes up and down. But it's telling you the average, right? Okay, so then what's the instantaneous rate of change? The instantaneous rate of change is when you pick a single point and you draw your slope indicator. That is a tangent line. Tangent means that it touches the function at one point only. And a tangent line, it's just kind of, it's like you bring a ruler down to just touch the function. That's your tangent line. And it's at a single point. So instantaneous rate of change is the tangent slope at a single point. So just to point out, what's the slope formula again? The slope formula is y2 minus y1 over x2 minus x1. How many coordinates do you need to do this formula? Well, you have 4 variables, but you need 2 coordinates, right? So the slope formula calculates what? The average rate of change or the instantaneous rate of change? Yeah, the slope formula itself calculates the secant slope, the average rate of change through 2 points. Do we have a formula that calculates the point, the slope at a single point? We do not have a formula for that, which is what created the need for calculus. Calculus was invented in order to come up with a formula to find the slope at a single point, a tangent point. Because we've had the slope formula through 2 points for centuries. Well, thousands of years, right? We know how to find the slope between 2 points. But to find the slope at a single point, that's what calculus was invented for. Because the slope formula needs 2 points, but we want to find the slope at 1 point. So it's very important. Okay, so let's go ahead and take a look at our, I wish that my board were cutting that problem down. Oh well. So it says, use this graph to evaluate the average rate of change of f, that is the function f. This whole thing is function f, right? That whole graph is function f, from 2 to 4. Now, what does that mean, from 2 to 4? Does that mean from 2 to 4 on the x-axis or from 2 to 4 on the y-axis? It is 2 to 4 on the x-axis. What they're really saying here, write it down underneath, is from x equals 2 to x equals 4. They're saying, find the coordinate on the graph that's at x equals 2. So where's the coordinate at x equals 2? Right here. So that's one coordinate, 2, 0. Find the average rate of change from that point to where x equals 4. And where's the coordinate when x equals 4? Right there. 4, 2. So first of all, that's just how to read the problem. The problem says, use the graph of f to evaluate the average rate of change, which we know is the secant slope, through 2 points, which really is just the regular slope formula of the function f from 2 to 4. And when we say from 2 to 4, we're always talking about the x-axis from 2 to 4. So from 2, that is the coordinate at 2, to 4, that is the coordinate at 4. Now we just have to find the slope. And that's it. That's all the problem is asked. The problem just says, what's that slope? And you can all calculate that doing the up-down over the right leg. You don't even have to do a slope formula. Just do the up-down over the right leg. How far up do you go? How far right do you go? And therefore the slope is up-down over right left. The slope is up 2, right 2. It simplifies out to 1 over 1. That's it. Given that that problem is so wildly easy, the only thing that was really new is learning all this vocabulary, right? So use the graph of f, that's it, this is the graph, this is the function f of x, to evaluate the average rate of change, which is the secant slope between 2 points, which is just the normal slope formula. The average rate of change of the function from 2 to 4, and then you x equals 2 to x equals 4, which means you have to go find those coordinates. Any questions about that problem? It's largely vocabulary building, so we know the language of calculus. They give you another problem. It says, now, find the average rate of change of f from 0 to 5. So go and do that on your own. Find the average rate of change from 0 to 5. Again, it wouldn't hurt to remind yourself, what do we mean? We mean from x equals 0 to x equals 5, where are those coordinates? When x is 0, what's y? The coordinate's way up there, right? And when x is 5, where's the coordinate? It's on my silly board. Here, I'll move it down. When x is 5, it's like right there. Did I do that right? There we go. So that's what we're talking about. Find the average rate of change of the function from 0 all the way to 5. So we're going from here to here. And we're finding that average rate of change. And again, you can just do this visually. You can say up, down, over the right, left. How far down do you go? And how far right do you go? And therefore the slope is, yeah, negative 1/5. Okay. Yeah, you always want to do the up down first. Thank you for pointing that out, Rosa. You'll notice that in my drawings, you could say, well, couldn't I have drawn it like that? And I would say, no, don't draw it like that. Because this looks like you're doing the right left first, followed by the up down. And how do we read a fraction? From top to bottom. I always read from top to bottom. So it's better to draw your arrows, you do the up down part and then the right left part. Those are things. Yeah, thanks for asking about that. Okay. Moving on. Next question. Now, we have lots of word problems in this class. We have a lot of word problems in this class because it's a business class, and so they're going to hopefully give us lots and lots of business applications. So, here we have the following chart shows the living wages. What's a living wage? Yeah, your salary, and from the amount of money you're earning from that salary, you hopefully are You're making a living, right? You're surviving. You're not going deeper and deeper into debt, but you're actually making a living. So this is in Rochester per 1,000 working age adults over a 5-year period. So let's look at what this data means first of all. So this is the year. It is a 5-year period. 1, 2, 3, 4. Well, no, sorry, 5 years. There we go, 5 years. And this is the number of living wage jobs per 1,000 working age adults. So just imagine, in 1997, out of 1,000 working age adults, only 645 of them were making a living wage. So what about the other 355 people? Yeah, now you might say, well, they were eking by, or no, they were in poverty. Well, maybe they just had a part-time job because they were in school. Right? Who knows? There could be a lot of different things. But the point is 645 of them were working in such a way that they were making enough money to live. Okay, so what do they want us to do about this? First of all, just look at the data. How many jobs, what happens over time? Yeah, more and more and more. So that could either mean that there were more and more jobs being created in the community, or it means that more and more people were switching from part-time work to full-time work. There's a lot of different interpretations. Okay, so overall, what is the slope of job growth going to be? Yeah, positive, right? Because the jobs are going up over time. Now, it says here, what is the average rate of change? So again, what is that from the definition at the top? The average rate of change means the secant slope between 2 points, which means we're going to use what formula? Up, down, to the right, left, and just the normal slope formula, right? I'm just talking about normal slope. We're not doing calculus yet. This is just normal slope. So what's the rate of change in the number of living wage jobs from 97 to 99? So we're going from 97 to 99. So now the question is, how do we take those numbers and plug them into this formula? At first glance, it might not be obvious. For instance, which column is the x and which column is the y? Are you sure? It was a good guess, you're right. You are correct, it was x, y. But now, how can we really be sure? What you always want to do, we start every problem by making a graph. So if we make a graph, what makes more sense? To put the years on the x-axis or the jobs on the x-axis? Years, time almost always goes on the x-axis because we're always following things through time. So it does make sense. So what we would do is we can just put 97 anywhere. And then we're going to go to 98, then we'll go to 99, then we'll go to 2000, and then we'll go to 01. So those are our years. And then we would want to put some sort of y-axis there. It's between 600 and 800. So I'm just going to arbitrarily put 600 here, 800 here, and 700 here. Now, the first thing you'll notice about my graph, other than maybe you're like, geez, kind of sloppy. But I'm playing kind of fast and loose with my axes, aren't I? Did I start my year at like 0 BC, birth of Christ? No. Did I start at 1990? No. I just went ahead and put down the years that interested me. And furthermore, up here, I didn't bother counting up from 0, 100, 200, 300, 400. I just put down the years that interest me. And that's fine. So now let's go ahead and just put in some dots, shall we? So 97 was 645, that's about there. 98 was 200, that's about there. 99 is 740, that's about there. 2000 is 770, that's about there. And 2001 is 790, that's about there. We call this a good sketch. Right? Like, would you present this at a business meeting? Probably not. You'd probably make a better graph if you're presenting to business people. But does it not carry all the information we need? It does. It's a really good graph. I call this a really good graph. Right? Because it's going to help us get the job done. Okay, so obviously the slope is positive, which is what we predicted. So now we just need to have these two coordinates. So I have my coordinate at 97, and I have my coordinate at 99. I can go ahead and write down my coordinate. So that's 97, 645. And then this coordinate was 99, 740. Now, what about the fact that I shortened all these to 97 and 99? Do I need to go back and call it 1997 and 1999? Maybe, if I want my graph to look a little better. But when I subtract, when I do my slope formula and I do 99 minus 97, the answer is, if I do 1999 minus 1997, the answer is, it's true either way, right? I'm just making my life easier. Again, I'm just making the graph be what I need to, so it has the information I need without doing extra work. Okay, so there we go. We're ready to do our slope formula. So you can go ahead and label x1, y1, x2, y2. Never hurts to label more than less. For clarity, you might say it hurts my hand, but no, it's always better to label more than less. So y2 minus y1, we have minus minus, write it empty. y2 is 740 minus 645. x2 minus x1 is 99 minus 97. And there we go. We can almost do this off the top of our head. I think it's 95 over 2. Now, is 95 divisible by 2? Not even, right? But could we simplify it anyway? We could call it 47.5 over 1. We still want to keep it over 1 because slope's a fraction. Furthermore, remember what are our units? So the top, the numerator is the change in y. What's our unit on the y-axis? Jobs. And what's our unit on the x-axis? Yeah, years, really, not just time. So now we can go ahead and say something. This is 47.5 jobs per year. Now we have come up with something very interesting. The question was, what is the average rate of change in the number of living wage jobs from 1997 to 1999? The answer is, the city has created 47.5 more living wage jobs on average per year. Well, did the city create the jobs or did people just take the jobs? Who knows? I guess you could just say that the number of living wage jobs has increased by 47.5 per year. That's it. And we're done. That's the whole problem. So everyone in the room, go ahead and do the second problem on your own. I'll just walk around, see your work. You do not have to draw a whole new graph. We already drew a graph. You're just going to go ahead and do another slope formula. By the way, when we take a pause, to work on a problem, you can feel free to talk to your neighbors, see what they're doing, compare notes. Seeing a little variability in answers. I think most of the answers are in the No, I'm not quite sure. Is it about 25? Is that what I'm seeing? 25 jumps per year? Let's just check. The average rate of change from what year? 99 to 2001. And see, now notice, I'm showing a lot of work, aren't I? I'm showing all my work. But in the long run, once you start getting comfortable with slope, I can just kind of look and say, okay, there's 99, there's 2001. I know it's 790 minus 740. And I know it's 01 minus 99, which is 2 years. And so then I can just go ahead and say 50 over 2, which is 25 over 1. Now you see what I just did, though? By not writing down the formula, by not labeling my coordinates, by not plugging it in very carefully, could I have just made a mistake? Yeah, I'm more likely to have just made a mistake. And furthermore, could someone else follow my work as easily? No. It's probably very confusing. Why'd you put a 2 down there? And then the bottom was dates and years. What's happening? Okay, so in any case, ladies, you all get 25 over 1? 25 over 1, what? Jobs per. Very good. Okay, fantastic. Any thoughts, questions, feelings about that? Okay, let's keep going. Now, this next problem will be a little more challenging. To which I'm sure you're all saying, good, great, I wanted that challenging stuff. Let's get to the challenging stuff. So, it says here, for each value below, enter the number correct to 4 decimal places. Okay, now 4 decimal places is what more requires. When you're on the more website and it's a decimal answer, they want 4 decimal places around for the 4th digit. So let's just call that a standard that we'll always have 4 decimal places in our work. So suppose an arrow is shot upward on the moon. Okay? So here's an arrow. Beautiful arrow. And it's shot upward, and then it comes back down. Right? So we can all imagine going to the moon with a bow and arrow upward and shoot an arrow and watch what happens. So it's shot with a velocity of 34 meters per second. I don't know if that's important yet, but the velocity equals 34 meters per second. And the height in meters after t seconds is given by that function. So apparently our x-axis is going to be time in seconds. And let's see here the height in meters. So this is now height in meters is given by that particular function right there. So that function is telling you the height of the arrow after t seconds. First of all, how does everybody feel about my drawing? And I hope you made a similar drawing. Right? Because we start every problem with a graph. We start every problem with a graph. What?
Graphing these.
Oh, there are stamps that you can buy that are just stamps of graph. But the problem is, all of our graphs are going to be different with different axes and different. It's good to just get in the habit of making a quick sketch. Like just a quick sketch. It doesn't have to be perfect. It doesn't even have to be really good. It just has to be good enough to capture all the information we just read. And I hope you all agree that my graph captures all the information that we just read. Start from the beginning. Suppose an arrow is shot upward on the moon with a velocity of 34 meters per second. Its height in meters after t seconds is given by that formula. So find the average velocity over the given time intervals. So let's just talk real quick about an arrow. If you shoot an arrow upward at 34 meters per second, first of all, how fast is that? I don't know, roughly 70 miles an hour. Because I think for the conversion from meters per second to miles per hour, it's just more than double. So let's just more than double it, 34 double to 68, let's call it 70 miles an hour. Is that a fast arrow, 70 miles per hour? I wouldn't like an arrow to come out 70 miles per hour. I wouldn't want a car to come out 70 miles per hour either. So 70 miles per hour, the arrow's going up. So what's going to happen to that arrow? It's going up at 70 miles per hour right now. Now, is the arrow here still traveling at 70 miles per hour? No. And what about at the top? Is it still going 70 miles per hour? No, it has slowed down considerably. Is the arrow going 0 miles per hour? No, because it's still moving sideways, right? If I had shot the arrow straight up, that would be different. Because at the bottom, it'd be going up at 70 miles per hour. And then around here, it's probably only going up still at 30 miles per hour. But at the time it gets to the tippy top, how fast is it going? 0, because it's stopped, and then it's going to come back down. Okay, the key thing is, though, our arrow starts out going fast, and then slower, 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 and then what happens? It starts going faster and faster and faster again as it comes down, right? So we can all imagine that even though this graph shows height, okay, the arrow is getting higher and higher and higher, and then lower and lower and lower. The velocity starts out fast, and the velocity gets slower, 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 and then faster, faster, faster. Okay? This is an important way to begin every problem. Draw a picture, understand what's happening, and be able to describe it. So that's what's happening to our arrow. So they say find the average velocity over the given time intervals. So for instance, consider the time interval 3 to 4. So everybody go ahead, let's just go ahead and choose. I'm going to call this 3. I'm going to call that 4. I just arbitrarily decided to put 4 underneath the apex and 3 a little to the left. And what we're saying is find the average velocity from here to here. That is a slope. We're going to find the average secant slope through those 2 points. That is what we're about to do. Now keep in mind, the units on this graph are height and time. Is the unit of this graph velocity? The unit of this graph is height. However, when we find a slope, keep in mind a slope is change in y over change in x. What's our y unit? Height, which is technically a distance. And what's our x unit? Time, which is a time. And what's distance over time again? A rate or a speed or velocity. So when they say find the average velocity of the arrow, they're asking you to find slope. Right? This is interesting to follow this all the way through. Okay, they didn't give us any information about velocity, but what they did was give us a graph whose slope is equal to velocity. So they're saying find the slope from that point to that point, and that will tell you that slope will tell you the average velocity of the arrow. Okay, so find the average velocity over the given time interval. So we have our picture, and finally, let's look at what this formula is going to look like. Okay, the first thing I don't want you to do is what I'm about to show you. And I'm going to show it to you to show you what doing too much work looks like. So let's say I actually wanted to find those coordinates, 3 and 4. Well, first of all, what's the height after 3 seconds? What would I have to do to find the height after 3 seconds? I'd have to plug in 3, right? Okay, so I'm going to take my calculator. I'm going to do 34 times 3 minus 0.83 times 3 squared, and that's 94.53. So the height is 94.53 when t is 3. Then what's the height at 4? What would I have to do? Plug in 4. So I'm going to hit second enter. If you hit second enter, it brings back up what I just typed, and I just go back and put a 4 where I had earlier put a 3. Okay, so now that's 122.17. Okay, so then that coordinate is 394.53, and this coordinate is 122.72. Okay, so you see how I got my coordinates? Now can I find the slope? Yeah, now I can find the slope. So if I really wanted to here, I would say, okay, my slope is between these 2 coordinates. So if I label x1, y1, x2, y2. So y2 minus y1, that's going to be 122.72 minus 94.53. And then now I have 4 minus 3. There we go. I'm almost done finding my first slope. So I have to do 122.72 minus 94.5. By the way, you can write this down. Right? We're not going to do this for every single problem. I'm going to show you a faster way. But we can start off by doing it that way. So that's going to turn out to be 28.19. All 4 minus 3 is 1, and therefore that's my answer. 28.19/1. I didn't have to write that twice. What's my unit? Meters per second. That's meters per second. And remember, how do you convert from meters per second to miles per hour? It's just more than double. So 28 doubles around 56. Let's just call it 60 miles per hour. Okay, well, we just did it, right? What does that mean then? They said find the average velocity over the given time intervals. So that means between 3 and 4 seconds, how fast was the arrow moving on average? How fast was the arrow moving on average? 60 miles an hour or 28.19 meters. Keep in mind though, when was the arrow moving faster, here or here? The arrow was moving faster here. And then by the time it got to the top, it was moving slower, right? So to be fair, the arrow was moving faster than slower, 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 slower. That's just an average. Right? It's not an average. That's not how fast the arrow was going here. It's not how fast the arrow was going here. It's the average of how fast the arrow was going over the time interval between 3 and 4. Okay? All right, well, so that's what we're talking about. That's conceptually what we just solved in this problem. Is by using a height function, we were able to calculate a slope, which calculated a velocity. That's interesting, right? Somebody gave us information about height, and we were able to figure out information about velocity. That's very powerful. Okay, so now what can we do to make this whole calculation faster? What I'd like to do is now show you, and this will be the little challenging here. Just find another spot to draw your graph. I realize I did it over here. I should have done that here. Find another spot to draw a graph. We're going to draw our graph. We're going to have some function called f of x. And we would like to know the average velocity from A to B. This is a very important drawing. When you go home tonight, I would draw this drawing 2, 3, 4, 5 more times, just to walk your way through the logic and the reasoning. So right now, I'm just looking at any function in the world, and I'd like to find the average slope between any 2 points A and B. So the first question is, in order to find the slope between 2 points, I need 2 coordinates. And right now, all I have is the x coordinate. How do I get the y coordinate? How do you calculate a y value? How do you calculate a height? Plug it into what? The function, right? So what am I plugging into f of x? A. So right here, the y value right there is actually f of a. And then what's my y value here above the b? I have to plug b into f of x, so now my y value is f of b. That might feel a little weird writing that down for the first time. But remember, what does f of anything represent? Height. It's the y coordinate. It's the y value. And what is it we want to write down? A coordinate. So I need my y value. And there's my y value. So what are the 2 coordinates? A, comma f of a, and b, comma f of b. First time you write that down, it might feel uncomfortable to think that that's the representation of a coordinate for any function. Okay, so now we have our 2 coordinates between our 2 time periods. Let's remember, we're going to call this x1, y1. And this is x2, y2. And I'd like to find the average slope, which means we're going to do the slope formula, y2 minus y1 over x2 minus x1. And therefore, we come up with this expression. What's y2? F of b. What's y1? A. And what's my x2? B. Next one. This expression right here is the general expression of the secant slope of any function. This is the general formula for the secant slope. Again, is the average slope of any function of x between any 2 points x equals a and x equals b. So we're going to use that formula. That formula calculates slope. Of course, that formula has to calculate slope because we started by writing m. M is slope. M equals the slope formula, which is this. And that's the average slope of any function between any 2 points. Now, I used f, but recall in this problem, they're using h. You can use f, g, h. All of those letters are used for functions. We're using h right now because we're representing a height. We're still using f, right? So now, let's write down all of these. Speedy. Instead of actually sitting here and plugging those numbers in and calculating them on my calculator, let's just write the general formula. The general formula, yeah, that's fine, I moved it. remember our general formula is, keep in mind that this is A and this is B. Right? That's our time interval. Starting on the left with A and on the right is B. So we're going to write down the formula, F of B minus F of A, all over B minus A. That's our general formula. We want to become very familiar with it, memorize it. And therefore, we can very quickly write down that the value of that slope, which happens to be velocity, is F of 3.5 minus F of 3. Oh, sorry, it's not F. We're dealing in H, aren't we? H of 3.5 minus H of 3 all over 3.5 minus 3. So let's keep in mind, this is a formula. That's why I was using F, because it represents any function in the universe. But concretely, what we're doing right now is dealing with this height function. So I switched to H, and I plugged in the seconds that they're referring to. So now instead of looking at 4 seconds, I'm looking at 3.5 seconds on my graph. So what we just wrote down right there is the answer. If you take your calculator and you plug 3.5 into this, and then plug 3 into that, and then subtract those and divide, it will give you the average velocity of that arrow. Now one nice thing is, without doing anything else, we can calculate the denominator very quickly. What's the denominator? It's 0.5. This is going to take a little effort, because you have to get out your calculator now. But before we do, let's just write it all down once so we can see how the formula and the pattern works. What about this velocity? Now, foregoing the formula, we don't have to keep writing the formula. Let's go ahead and now plug this in. This is the average slope from 3 to 3.1 on this graph is going to be h of 3.1 minus h of 3 all over 3.1 minus 3. That's the formula. And as soon as you type all that into your calculator, you'll have the average velocity of the arrow. Likewise, for this time interval from 3 to 3.01. We can find the slope between 3 and 3.01 on this graph by just doing h of 3.01 minus h of 3 all over 3.01 minus 3. And then we can do that for this interval too. So we're going to do h of 3.001 minus h of 3 all over 3.001 minus 3. How does everyone feel about what we just did? I turned you into an assembly line. Like instead of getting bogged down into the details and the decimals up front, we just came up with a formula. Then we now just have a formula that we can use always to quickly calculate an average velocity, or I'm sorry, an average slope. Okay, so let's talk about calculator skills. How do we do this on our calculator now? Because I want you all to be fast and speedy with your calculator. So I want to teach you a couple things. So everyone take out your calculator. If you have a TI, great, because that's the instructions I'll be giving you. If you have a different type of calculator, probably you can figure it out on that as well. Likewise, an iPhone is going to be completely different. Do you have a calculator with you today? Okay, so maybe just watch, because the iPhone doesn't work like this at all. But on your TI, okay, what we're going to type in is, first of all, we're going to type in this formula at empty. So start by typing down 30, well, hold on. First of all, what does it mean to write it empty? 34 times something minus 0.83 times something squared. That's the structure we're going to put into our calculator, but with an actual number in it. So the first one we're going to type in, is 3.5. So everybody type this expression into your calculator exactly. And by exactly, I mean you have to type 3.4 parenthesis, 3.5 parenthesis, minus 0.83 parenthesis, 3.5 parenthesis squared. And if you have your TI with you, you can just walk around, hit your word. By the way, if you hit enter, it should be 108.8. So that's how you can check yourself. Did you get 108.8? Super. Did I get 108.8? All right. All right. Okay. So now, go ahead and write that part down, because we just got h of 3.5, so that's 108.835. Now, this is the magic part, because you might say, oh my gosh, Mr. G, we have to calculate all these decimals. And you're right, we do. But there's a way to do it quickly on your calculator. So now everybody pick back up your calculator, and I want you to hit second enter. second upper left, enter lower right. If you hit second enter, what happens? It just brings back up the same thing you just typed. So now all you have to do is hit your arrow button and go back and type in the number 3. Now to rewrite 3.5 with the number 3, you have to delete some stuff. But instead just write in 3.0. Because 3.0 is the same as 3. So now just go back and instead of 3.5, just put a 0 where the 5 was. And now you have 3.0, which is 3. So edit your equation, hit enter, and now you should all get the decimal 94.53. We're going to do all these calculations real fast. I'm going to show you how to do it quickly. So that's the first one. Now, what do you notice that each and every one of these formulas has? They all have h of 3. So go ahead and put all these fraction lines with your minus symbol, and you can go ahead and copy that number all the way down. 94.53 is part of all of these. So now, what do we have left to actually calculate on our calculator? H of 3.1, H of 3.01, and H of 3.001. So now let's do that. We can once again edit our formula to be 3.01. So again, hit second, enter, and now go back and change all those 3.0s into 3.1s. So now that gives me 97.97. Now I do have to teach you something new here, because to do 3.01, we need to create more space in the calculator. We're going to have to insert some more decimal digits. You can't just start typing in 3.01 because it'll overwrite the equation. You don't start all over. So again, hit second enter, and go back up to where it says 3.1 and put the cursor on the 1. So go back up, hit second enter again, bring up your equation where it's 3.1, and now what you do is you hit second delete, second del, because second del activates the word on top of it, which is INS for insert. So if you hit second del, your cursor flashes and you're ready to insert a digit in front of the digit you've highlighted. So now if you hit 0, I now have 3.01. And now I move my cursor over to the right, I put it on the 1 again, and I hit second insert, and I push a 0, and now my formula says 3.01. And that gives me 94.820117. Now you might say, Mr. G, all this calculator business, I'll just type it in every time. Right? But I'm trying to show you how to be faster. You don't have to type the expression in from scratch every single time. You can use your calculator. So now again, if you want 3.001, you'll once again hit second insert or second enter. That brings it back up, and now you go back, you put the cursor on the 1 again, you hit second insert 0, go back to the other one, 3.001, second insert 0, and now I've changed everything to 3.001, and that gives me 94.5590117. Okay, let's see, Mr. G, whoa, we just went way off on this tangent here. We're writing down tons of decimals. What are we doing right here? Well, we're solving a very lengthy problem. We're considering finding the average rate of the arrow on shorter and shorter time intervals. So we originally started the time interval 3 to 4, but then the interval 3 to 3.5, and then the interval 3 to 3.1, and then the interval 3 to 3.01. So we're looking at shorter and shorter time intervals. And consider what that means that we're finding. We are, instead of these 2 points, we're doing the slope from these 2 points. But then instead of those 2 points, we're doing the slope between these 2 points. And then we're doing 2 points that are right on top of each other. And eventually, we're choosing 2 points that are so close to each other. If you choose 2 points that are so close to each other, what does it look like to have? 1 point, which is a tangent slope, which is what we're trying to build toward. So even though we're finding secant slopes, we're trying to push those 2 points so close to each other that if we could get those 2 points infinitely close to each other, you would in fact be calculating a tangent slope instead of a secant slope. Okay, by the way, can we calculate all these denominators in our head? Yeah, 3.1 minus 3 is 0.1, 3.01 minus 3 is 0.01, and then 3.001 minus 3 is 0.001. Okay, now folks, you now have all the numbers that you need in order to actually now calculate each of those fractions. So now you have to go back, type in those decimals, calculate the fractions. By the way, folks, when you type it in your calculator, make sure you do parenthesis, that minus that, parenthesis, divide by 0.5. Because I see a lot of people do 108 minus 94 divided by 0.5. And what does that do? If you don't have parentheses, what are you doing? You're only dividing the 94 by that. And that's wrong. It has to be parenthesis, 108 minus 94 parenthesis, then divide by 0.5. So make sure you do that. Okay, I'm just about out of time here. Key thing is, we're essentially done with this problem. I need you all, for your homework for tonight, to go ahead and calculate each of those decimals and come back to class next time with this problem done so that we can look at it and review it together, okay? Now, we did not finish the entire packet of 2.1. And that's okay. We'll be able to finish it next time. We had, what, 4, 7, 8, 10? Yeah, there's just a couple problems left that we didn't do. So what that means is, again, I expect you to finish this problem, do all those calculations, get your decimal answers. We'll start back right here. When you come back on Tuesday, we'll finish the rest of these problems, and then we'll move on to section 2.2. The good news for all of you, because we didn't finish 2.1, is that it's not due on Tuesday. So I'm going to bump the due date a whole week, because I will never have you have to turn in an assignment before we finish it. So everybody just know that you have no homework due on Tuesday, other than finishing this problem. So everybody needs to finish calculating all these decimals and bring this back with you. Does anyone have any questions? Okay, well that's it. I think anyway. Yeah, we have 2 minutes. I'm here to help you. Especially with your calculator. If my instructions on the calculator was too quick, and you want to say, hey, Mr. Drew, you just show me how to use my calculator, I'll show you. Do you want me to show you how to use your calculator? Okay. Oh, great, yeah, we do. So we have all that. So you put 23 parentheses, and that's fine. And then you got, so like here, if you're doing 3.5, there it is. Oh, so you want to change that one to a 0. So now you're doing, that is a 3.0, and that's a 3.0. So that would be the decimal for 3.0. And then you have to change both. Yeah. So now hit second enter again. And let's say I want to change 3.0 to 3.1. So I go up to the 0. Actually, you know, 3.1 as well. So if you change that to 3.1, and then that's 3.1. So that's another decimal value that you need to oh, you did it over here. Okay, yeah, that's fine. So you're going to need 3.1 somewhere. So there's that. But then you need 3.01. So you hit second enter again. And then you put your cursor on the 1 and you hit second delete, which is INS for insert. So now the cursor is blinking, and I put 0, and it shoves in a 0. And I come back over to here. Well, delete would be if you want to delete digits. But I hit second delete because I want to insert digits. So right now, again, that's a 0.1. I hit second insert, and now I can insert a 0, and now it's 0. So now I just calculated that whole expression with 3.01. Now watch, I want 3.001. So again, I hit second enter to bring it back up. And then I go up to the 1, I hit second insert, and insert another 0. Now it's 3.0. Okay, so watch. If I just go here, right here, and I just put 0, it just overwrote the 1. And now if I push 1, it overwrote the parenthesis. And now I would have to retype in the whole formula. If you don't do second insert, it just starts writing over what you have. So watch this. So as a for instance, if I start right here and I hit second insert, I can put in as many zeros as I want. And it kept the whole word square. Now if I go back, I just hit delete, deleting all those zeros. Now, if I don't hit second insert and I just start hitting zeros, it just overwrites it. So we don't want to overwrite it. We want to insert that. So again, I have to go back, delete all those zeros. If you just want to type each one, that's fine. That's totally fine. If you just want to type it, that's fine. That's fine. That's totally fine if I type it. You can just type it. Oh, okay, for which one? You did it. So from D to C, here's D and here's C. Now let me press your pencil. So from D to C, remember, up, down, right, left, you always do the up, down first. So if I'm at D and I need to get to C, I need to go down. How far down did I go? Here. Now I need to go right, left, I have to go right. How far? 1, 2. Okay. So down 3, right 2. You always start with the up, down. Not down, the up down. You always start with the numerator, which represents up down. So like for instance, let's say I wanted to get from N to K. To get from N to K, I need to go down and then right. Importantly, you do the vertical motion first, and then you do the right horizontal. So from N to P is from here to here. And so already you should just know from memorization that that's a zero slope. But remember, look right here, that's positive, that's negative, that's zero. Count. So it'd be up nothing, because you're not going up at all. So that'd be up nothing. And then you go right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what's 0 divided by 10? Type it in. What's 0 divided by 10? Well, try it. 0 divided by 10. 0. And that's why it's 0. Okay? And then this one, you want to see again. What? Because, yeah, well, I don't know that I put the 1. I think it was a 10. Up 0, right 10. Yeah. But maybe we put 1 because it's 0 over 1 as a fraction. 0 slopes with a 0 over 1. And then from C to A, it's just straight down. So you go down 4, right nothing. So down 4, right nothing. And what's 4 divided by 0? 4 divided by 0. Error. That's why it's undefined. Yeah. Keep going. I'm not going anywhere. I'm just going to close up some shop here. Rosa, you have any more questions for me?
No.
Okay. Henry, any more questions?
So I put the function in the area that
Yeah.